In this videotape, you will see a proper method of determining the feeds and speeds you will need to efficiently machine ferrous, non-ferrous, and plastic materials. After viewing this videotape, you should be able to list the safety procedures that are required in every machine shop, as well as those involved with feeds, speeds, depth of cut, and tool selection on the lathe. Write down the sources of information for finding formulas, cutting foot speeds, and tool selection for machining operations on the lathe. And write down the formulas and use the charts to determine correct feeds and speeds for setting up a lathe to operate more efficiently. When you are working in the machine shop, you have to take some precautions to protect yourself and the people around you. Always wear your safety glasses. Remove your jewelry such as rings and watches. Keep your sleeves above the elbow. Never remove chips from a turning workpiece with your fingers. If necessary, use a pair of pliers. Know the capacity of the machine, so you will not overload it by taking too heavy a cut when turning. All of your machining operations will be performed on materials made of either ferrous metals, non-ferrous metals, or plastics. Ferrous metals are metals which contain or are derived from iron. Tool steel and machine steel are examples of ferrous metals. Non-ferrous metals do not contain any iron. Lead, tin, and aluminum are non-ferrous metals. Plastics are non-metallic materials which are synthetically produced. Some of the trade names under which plastics are sold are lucite, plexiglass, and bakelite. The cutting foot speed for a material, which is expressed in feet per minute, is an important consideration for any machining operation. On the lathe, this refers to the number of feet the outside surface of the work revolves past the cutting edge of the tool in 1 minute. The cutting foot speed of a material, or CFS as it is abbreviated, is affected by the RPMs of the work and the diameter of the work. In order to keep the cutting foot speed constant, you have to adjust the RPMs as the diameter of the workpiece changes. The type of cutting tool you use also affects the cutting foot speed. For example, a high-speed steel tool bit will have a lower cutting foot speed than a cemented carbide cutting tool. For this reason, you have to take note of the type of tool bit you are using when selecting the cutting foot speed for turning on the lathe. Before demonstrating the theory of cutting foot speed, you need to know how to use this basic formula to find each of these factors when the other two are given. Cutting foot speed is equal to circumference times the RPMs. RPM is equal to cutting foot speed divided by the circumference. And circumference is equal to the cutting foot speed divided by the RPM. Imagine this piece of string as a continuous chip formed by a workpiece passing the point of a cutting tool. You can make the following assumptions for this demonstration: that the cutting foot speed on this material is 25 feet per minute, and the workpiece is 2 inches in diameter. You should remember that the circumference of a circle is equal to 3.14, or pi, times the diameter of the circle. Therefore, the circumference of the piece in this demonstration is equal to 3.14 times 2, or 6.28 inches. You can now find the RPM, since you have the values for the cutting foot speed and the circumference by using the formula RPM is equal to cutting foot speed divided by the circumference. However, a word of caution. You must always be sure that the cutting foot speed and the circumference are in the same units. Since the circumference is given in inches, you can convert the cutting foot speed to inches per minute by multiplying by 12. The formula now reads RPM is equal to 25 times 12 divided by 6.28, which is equal to 47.8. You would arrive at the same results if you converted the circumference to feet. With the calculation completed, we will now demonstrate the cutting foot speed rule. First, set the RPM at 47.8. A piece of string is wound around the 2-inch diameter workpiece in the chuck. Start timing as you unwind the string from the surface of the work. After 15 seconds, stop the machine. Now measure the length of the string. The string measures 6 feet 3 inches. Multiply by 4 to get the cutting foot speed. So the surface speed of the work is 25 feet per minute. If you want to maintain a cutting foot speed of 25 surface feet per minute for a smaller diameter workpiece, you must increase the RPM. Here is a 1-inch diameter workpiece. Therefore, the circumference is 3.14 times 1, or 3.14 inches. Convert the 25 feet per minute to inches per minute by multiplying by 12, which equals 300. This puts both factors of the formula in the same unit, inches. Now you divide 300 by 3.14 to yield an RPM of 95.5. As you can see, the 1-inch diameter must run twice as fast as the 2-inch diameter to produce the cutting foot speed of 25 feet per minute. The other factors which influence the selection of your cutting speed are: 1. The material you are machining. Hard material requires a slower cutting speed than soft or ductile material. 2. The tool material you are using. Cemented carbide tools can be used at higher speeds than high-speed steel cutting tools. 3. The operation you are performing. Forming operations require slower speeds than general turning operations. 4. The feed rate and depth of cut you are using. Heavy roughing cuts require slower cutting speeds than light finishing cuts. 5. The coolant or cutting lubricant you are using. Generally, using coolants and lubricants on ferrous metals allows for higher RPMs and prolongs the life of the tool. And 6. The power and condition of the machine you are using. Higher cutting speeds may be used on heavy machines that are in good repair. The figures that you see for feeds and speeds on charts and calculations have already taken these factors into account. You calculate the RPM for your machining operation by following these steps. First, determine the machining operation and the type of material you will be machining. With these factors, use the chart to find the appropriate cutting foot speed. Use the cutting foot speed to determine the RPM either by using the calculator, by using the formula cutting foot speed times 4 divided by the diameter equals the approximate RPM, or by using the appropriate chart in the machinery's handbook. To use the calculator, let's use a cutting foot speed of 100 and a diameter of 2 inches. Set the work diameter under the arrow. Now read the RPM, which appears directly above the 100 foot per minute reading. The calculator shows a reading of approximately 192. Using the formula cutting foot speed times 4 divided by the diameter equals the approximate RPM, you get 100 times 4 divided by 2, which equals 200. Using the machinery's handbook, look in the index under speeds. and turn to the appropriate chart. Find your cutting foot speed of 100 and move down the column to the 2-inch diameter. This shows an RPM of 191. As you can see, the results using all three methods are within 10 RPM. The lathe may not have that fine an adjustment for RPM, so a setting of between 180 and 200 is acceptable. A variation of plus or minus 10 RPM will not significantly affect the machining operation. Feed rate refers to the distance the tool advances for one revolution of the work. There are 4 factors which govern the selection of the feed rate you use. Number 1, the rigidity of the work and the manner in which it is held. You use a coarse feed for large, rigid work held securely in a jaw chuck or between centers, and a fine feed for long, slender work held in a collet chuck. 2, the finish you desire. A coarse feed for a rough finish, and a fine feed for a smooth finish. 3, the depth of cut you desire. A roughing tool, by the geometry of its construction, takes a deeper cut than the finishing tool. A handy rule for determining feed rate is to take 1/10 the depth of cut. And 4, the shape of the tool and the operation you are performing. You reduce the feed rate for all finishing operations. You can determine the feed rates for different materials and different kinds of cutting tools from charts and calculations. However, this skill is developed through knowledge and experience in operating a lathe. Let's demonstrate the feed rate principle. You can observe feed by the movement of the carriage. Set the feed rate at 10 thousandths by positioning the lever on the front of the quick change gearbox. Set the RPM to 100. Start the spindle. Make a pencil mark on the ways to indicate the end of the carriage. Start the automatic feed of the carriage and a stopwatch at the same time and allow them to run for exactly 1 minute. Now multiply the feed rate of 10 thousandths by the 100 RPM, and this should give you the distance the carriage traveled. As you see, the measured distance of 1 inch and the calculated distance of 1 inch are the same. The cutting tool will therefore move 1 inch divided by 100, or 10 thousandths of an inch for each revolution of the work. This is the same as the setting on the quick change gearbox. Besides feeds and speeds, you need to know how depth of cut influences your machining operations. Depth of cut is usually determined by considering such factors as tool geometry, rigidity of the work, surface finish you desire, and the amount of material you wish to remove from the diameter. By grinding a roughing tool to the proper relief and rake angles and a chip breaker, you can take heavy depth of cuts without damaging or destroying the tool. The finish you will receive from this kind of operation will be very rough when compared to a lighter cut using a finishing tool. You cannot get both the heavy depth of cut and the smooth finish with a finishing tool, because large amounts of tool contact with the work would produce too much heat and destroy the tool. As you gain experience, you will be better able to determine the most efficient means of removing material. You can sometimes save time in machining by making 2 cuts with a finishing tool instead of a roughing cut and a finishing cut. Remember that setting up a different tool bit takes time. Most new and inexperienced machinists seem to be overly cautious in machining by setting too slow a feed rate and too light a depth of cut. Remember, too light a depth of cut increases your machining time on the job, and in industry, time is money. In review, you should now be able to describe the shop safety procedures, Write down the sources of information for finding formulas, cutting foot speeds, and tool selection for machining on a lathe. And write down the formulas and use the charts to determine correct feeds and speeds for setting up a lathe to operate most efficiently. You have been shown the very fundamental concepts of feeds and speeds, which you need to know in every lathe operation.